Okay, we are talking about the Doppler effect. And the Doppler effect. And what the Doppler effect is, I'm going to define it first and then explain it. It's an apparent change in frequency of a wave caused by relative motion between the source of the wave and the observer. Okay, by relative motion, that just means that between the two of those things, there's movement between them. So what wouldn't be relative motion is if you were on a train and that train is moving 50 miles per hour. Because you were on the train, you were also moving 50 miles per hour. Okay, so there's no relative motion between you and that object that's making that noise. So the thing that's making the noise, we call it the source. The person that hears the noise or the sound is the observer. Okay, so before we get into exactly what the Doppler effect is, we're going to talk about what you actually hear when we talk about frequency. So instead of drawing a longitudinal wave, I'm drawing a transverse wave because it's easier to see. Okay, this is a transverse wave. And when there's a change in the amplitude, this is the amplitude, what you hear for amplitude is the loudness. Loudness. That's how loud it is. So when you get an amplifier or you're close to an amp at a concert, you really hear that a lot. It's amplifying the music. It's making it louder. Okay. If we have a change in frequency, so a change in frequency would mean that the wave is more frequent. Okay. And what you actually hear when you hear frequency is you hear a change in pitch. So the greater the frequency, the higher the pitch. Okay, so that's what we're talking about. So let's say I have a police car. Okay, and this police car, the sirens are on, and when the sirens are on, it's emitting sound waves. So I'm going to draw the sound waves, and those waves are longitudinal. Okay, so the longitudinal reminder means that the waves are moving parallel to the wave motion. Okay, the particles are moving parallel to the wave motion. So here's your first sound wave. Here's your next sound wave. And by the way, this police car, I said it already, is stationary. Okay, so these sound waves are pretty evenly, when they're getting emitted evenly, and there's an even space, this is your wavelength, between each sound wave. I'll draw another one. Okay, so my wavelengths are all equal because this thing is stationary. Okay, so now instead, let's say this is stationary, so these wavelengths are all evenly spaced. Let's say in a different scenario. So we have a moving police car. Okay. Here are the sirens. And let's say you're over here and you are the observer. And this obviously is the source. And it's moving towards you. And this might seem like common sense, but this is just an explanation of it. As this is emitting sound waves. It's also moving. So really, as it's moving, the sound waves are kind of catching up with each other. Okay, and I'm not really drawing this well because what's happening is, I'm going to erase some of this, is those waves are getting closer together. Okay, can't erase here. Okay, so let's say this is your first one, and this is your next one, and then your next one, and then your next one. Okay, so these sound waves are getting closer together. So that means the wavelength between each wave is getting smaller. Okay, so because it's kind of catching up with the next wave. Okay, it's getting closer and closer, and what you hear is something a little bit different. So we know this good old equation, and V is the speed of sound. Speed of sound, and that number is fixed, considering that the temperature is probably constant during this time. Speed of sound, that's fixed. If my wavelength is getting smaller, that means my frequency to compensate has to be getting larger. Okay, and a greater frequency is a higher pitch. So as this police car approaches you, you hear a higher frequency. And then as it leaves you, those wavelengths, let's say you're on this side of it now, and those wavelengths, what's happening is they get farther apart from each other. And what you hear is you hear a lower frequency as it goes away. Okay, and that's what the Doppler effect is. It's an apparent change in frequency of the wave caused by a relative motion between the source of the wave and the observer. Okay, so I want you to think about the example I said. Let's say instead of a train, you're in the car with your partner, okay? And your partner decides to blast the horn, and you're sitting in the car. So because you and your partner are both moving, so here's your car, and you're in here, you're the observer, and the horn is blasting, that's the source. Because you and the source are moving at the same speed, there should be no change in apparent frequency, okay? Because there's no relative motion between the observer and the source. Let me show an example of what that sounds like.
Hi everyone, we are going to do our experiment. I am the observer and the horn is going to be the source. Kaylin, do you want to say hi?
Hi.
And there's Nyan, you can see him in the mirror. Here's Mr. Pietrick. Okay, so we're gonna hit the horn and see what happens. See if you can find a change in frequency. Okay, go ahead.
Okay, so you saw that, and you saw that I was in the car, and you should have heard no difference between the frequency of the source and what you actually heard. It should have sounded the same because we were moving together as one unit, right? So now in the next video, I am the observer, and I'm going to be standing outside of the car, and the car is going to pass me. So I want you to pay close attention to the change in frequency as it approaches me and then as it passes me.
The car's gonna drive by me while blasting the horn. Okay, so see the difference or hear the difference between the frequency as it approaches me and then as it passes me. Okay, here it comes. And there it was. You could see the change in frequency. As it approached me, it got higher, and then as it left me, the frequency got lower. Bye.
Okay, so similarly, let's say, we could have done this in the car as well, but we didn't. Let's say, here is the car. This is the SUV. I don't know. Don't judge me on my pictures. And it's stationary. So it's stationary, which means it's at rest. But let's say my husband is blasting the horn. So this is still the source, okay? And this time, here I am, I'm the one who's walking towards it, okay? As I walk towards it, it's the same situation, it's pretty much the same concept. As I walk towards it, what I see is I see these waves get bunched up closer together, okay? So whenever two objects get closer together, what we're going to hear is that we're going to hear a higher frequency, okay? But now let's say I pass it. Whenever two objects get farther apart, what the observer will hear is a lower frequency. Okay? I'm going to show you guys a clip from a TV show. So it's a couple-minute clip, so I want to add this in here because it kind of makes sense now that you maybe know what the Doppler effect is. Okay?
Okay, bud.
Okay, so we're going to wrap up with the equation finally. So what I have here is your equation for the Doppler effect. Frequency of the observer equals frequency of the source, V plus or minus V observer, all over V minus or plus V source. Okay, and I'm going to explain everything, so don't worry, don't panic. Okay, so V this V is the speed of sound. And unless the problem gives you a new speed of sound, we're always going to assume that this speed of sound is going to be 343 meters per second. Okay. The free FO, that means frequency of the observer. So this is the frequency the observer hears. Sometimes you'll see this as detected frequency. And this is in hertz. Okay, that's this thing right here. Fs is the frequency of the source. This is the actual frequency. So this is the horn, let's say sirens, or a screaming person who's walking by you, maybe, I don't know. Okay, that is also measured in hertz. Okay. VO, I know we're used to seeing this as V naught, but this is actually the speed of the observer. Okay, how fast is the person who's listening actually moving? Are they stationary or are they moving? Okay, that's in meters per second. And then VS is the speed of the source. How fast is that source moving? Okay, so before we get into more about this, what is up with the plus or minus? Okay, I'm going to erase some of these highlights. What is up with the plus or minus? Okay, so you have to know your math here. This looks like a complicated equation, but it's really not. Okay, if things are getting closer together, if the observer and the source are getting closer together, they are going to hear a higher frequency. Okay, they are going to hear a higher frequency. So let me do this in a different color pen. If it's going to hear a higher frequency, it's going to be higher than the source. So that frequency, if they're getting closer together, the observer is going to hear a higher frequency. Now, whenever we think about a higher frequency, we need to consider what we want our numerator to be and what we want our denominator to be. Okay? If we want this to be a greater number, then we want a big numerator. So we're going to add in the numerator. And then if we want this to be a bigger number, a smaller denominator will give us a bigger value here. Okay? So those are the two you're going to use. Those are the two signs you're going to use if this is getting closer together. Okay? Now, I'm going to write this equation again. V plus or minus V naught over V plus or minus Vs. Okay? Now, let's say the source and the observer are getting farther apart. So let's say the source has already passed the observer and now it's moving forward. Okay? That means the observer is going to hear a lower pitch sound. So this is going to be lower. Okay, so that means we want this to be a fraction that's less than 1. So we want a small numerator and a big denominator. Okay, think about that, what you think that means mathematically, and we're going to do an example. Okay, here's your example. Let's say here is a truck, and this truck is traveling at 27 meters per second. Okay, and I have a hitchhiker here. Here they are, they're trying to get a ride. I don't think people do that anymore, that's dangerous, you shouldn't do that. Okay, they're pretty sad they don't have a ride and they're stuck on the middle of the road. And they're standing there. So standing means that their velocity, if they're at rest or they're stationary, if they're standing there, their velocity, this velocity of this person is 0 meters per second. Okay. The truck is not going to pick up this hitchhiker. They're kind of annoyed that this person is standing on the side of the road. So instead, they're just going to honk their horn. Okay, so they're blasting their horn. Horn. And that horn is blasting at a frequency of 400 hertz. Okay, and this is the source, by the way. Okay, so you have two parts to this question. What does the hitchhiker hear as the truck approaches the hitchhiker? And what does a hitchhiker hear as the truck passes the hitchhiker? Okay, so before I solve this problem, I want to write down my knowns and unknowns. There's lots of things to write. So I know the frequency of the source is 400 hertz. I know the velocity of the source is 27 meters per second. I know the velocity of the observer is 0 meters per second. I know the speed of sound is that 343 number. So I'm looking for the frequency of the observer. And there's two parts. So as it approaches, I know that number is going to be bigger, right? As it approaches, so as it's coming nearer, it's going to be bigger. So here's my equation again. The frequency of the observer equals Fs. And, whoops, I got these mixed up. Sorry. Okay, as it approaches, I know I want a big numerator and a small denominator. Okay, I also know that my velocity of this is 0, so this just goes away. Okay, so I have 400 hertz, 343 meters per second, over 343 minus 27 meters per second. Do the calculation, you should get 434.17 hertz. This makes sense because this number is greater than the actual source, and that's what it should be because it's coming closer, so you hear a higher pitch than what's actually happening. Similarly, for the next part of the problem, as it passes, this is going to be minus on top, this is going to be plus on bottom, and I'm just going to plug the numbers in. Okay, again, this is 0, so I have 400 hertz, 343 meters per second, over 343 plus 27. You're going to do the calculation, you should get 370.1 hertz. Now, this also makes sense because this frequency that the observer hears is less than the original 400, and that should confirm that you did this correctly because they hear a lower pitch as the truck passes them by. Okay, so I will post the assignment. Hopefully you enjoyed this. Bye.